So exactly what's bond? What do we mean by when we say we have a polar bond? We said that's when the shared electrons spend more time near one of the two atoms. Okay. You can define what's called the bond dipole moment. It's a vector quantity, so it's got magnitude and direction as a measure of bond polarity. Okay, so bond dipole moment is given by the partial charge, okay, times 1.602 times 10 to the negative 19 coulomb. This is the charge of one electron, also the charge of one proton. It's negative for an electron, it's positive for the proton, times the distance r. Okay? So, in other words, if you imagine a proton and an electron separated by a distance r, okay, what would be your dipole moment for that? Then you'd have a full charge, okay, a full unit of charge. One electron is negative 1, one proton is positive 1. So delta is equal to 1 there, okay? It's full charge actually, so it's not a partial charge. Times the charge of the electron or proton, which is 1.6 times 10 to the negative 19 times r. That would be the dipole moment. But in a bond, okay, you say there's a partial charge between the two atoms. So you multiply the full charge. Your delta right here would be a number between 0 and 1. Okay, so that gives you what we call the ionic character of the bond, the extent to which electron has been transferred from one end of the molecule to the other. Okay, so R here is the bond length. So what's the unit for dipole moment? The unit is a debye. The official abbreviation for the debye is capital D. And it's 3.336 times 10 to the negative 30 coulomb meter. Okay, where does that unit come from? A unit of charge is a coulomb. SI unit for length is meter. So your unit for dipole moment is a coulomb meter. So here's an example. HF, the molecule HF, is experimentally found to have a bond length of 92 picometers. So if you have hydrogen and fluorine, okay, and you look at the separation of the two nuclei, the average separation is 92 picometers. So that's 92 times 10 to the negative 12 meters. And the experimental dipole moment can be measured to be 1.9 debye. So what's the partial charge of HF? How do you solve for the partial charge or the ionic character? What was our formula? Mu equals partial charge times 1.6 times 10 to the negative 1.602 times 10 to the negative 19 coulombs times R. How do I solve for delta? Divide both sides by this, right? So 1.602 times 10 to the negative 19 times R. So delta equals dipole moment 1.9 debye oops, sorry, 1.9 debye over 1.602 times 10 to the negative 19 coulombs times distance in this particular case is 92 picometers. So 92 times 10 to the negative 12 meters. What is the debye? You have to change that unit to SI. What's 1 debye? 3.336 times 10 to the negative 30. Coulomb meter. Okay, so debye cancels out. Coulomb and meter cancel out. So you just get your partial charge or ionic character. And that's equal to how much? You have a number for me? You should come up with about 0.43. Let's see. Okay, so 1.9 times 3.336 times 10 to the negative 30 divided by 1.602 times 10 to the negative 19 divided by 92 times 10 to the negative 12, 0.43. Okay? So we say that our ionic character is 0.43, or we say it's 43% ionic. Okay? So you might say that a transfer of one electron, a net transfer of one electron from one atom to another, we say is 100% ionic. But because the electron transfer is not complete, we say we have a polar bond, a polar covalent bond, which is only 43%. The electron is only 43% transferred from one to the other. So that's how you get a polar bond. So dipole interaction occurs when you have polar molecules, between polar molecules, and you can get a polar molecule if it has a polar bond. Okay? But it doesn't mean that if a molecule has a polar bond that it is polar, because if you have a molecule that has more than 2 bonds, it's more than 3 atoms, then those polar bonds could end up canceling each other out. So you may end up with a molecule that's not polar, even though it has polar bond. So when we say a molecule is polar, okay, it must have we say it has a non-zero dipole moment. The dipole moment for a molecule will just be the sum of all the dipole moments for the bonds, okay? So you get a polar molecule if your bond dipole moments add up to a non-zero value. They don't cancel each other out. So how can you tell if you have a polar molecule qualitatively? First of all, it has to have at least one polar bond, right? But if there's more than one polar bond, they must not be symmetrically oriented. For example, carbon dioxide is non-polar. If you look at carbon dioxide, here's a model for carbon dioxide. Oxygen is more polar than carbon, okay? I mean, it's more electronegative than carbon. So the CO bond, we say, is polar. So there's the carbon to oxygen is polar that way. This carbon to oxygen bond is polar this way. These polarities cancel each other out. So the vector sum of those two dipole moment vectors is 0. So even though carbon dioxide has 2 polar bonds, the molecule itself is nonpolar because of the symmetry. What about water? Here's your oxygen, and here's your hydrogen right here. You have a polarity towards oxygen. Okay, oxygen is more electronegative than hydrogen. So there's a polarity going that way, and there's another polarity going this way. Okay, so you can see there's a net polarity towards the oxygen end of the molecule. So we say that a water molecule is polar. Okay, so that's how you can tell if you have a polar molecule or not.